Gibbs-Duhem relationship and combine first and second law of thermodynamics. What we have learned so far, U equals to U hat SD du TdS minus PdV, and then we had Legendre transformation which had H hat and we transform V to B, and we have dH equals to TdS plus VdP. We had transformation of S to T, A equals to A hat PV, and we had dA equals to minus SdT minus PdV. Then we transform both. We had G equals to G hat TP, we had dG equals to minus SdT plus VD, right? Yes? Okay, fine. So you have du, dH, dA and dG. So all this combine first and second law of thermodynamics, and from here we implemented the thermodynamic property, which is, for example, what we have done: rho to U, rho S, rho V, which must be equals to rho to U, rho V, rho S. Okay? Which must be equals to rho to U by rho V, rho S. And with that, we got a couple of relationships. First relationship, so from here we got relationship which is rho T by rho V at fixed S minus rho T by rho S at fixed V. Then we got rho V by rho S at fixed P, which is rho T by rho P at fixed S. Then we have rho S, rho V at fixed T, which is plus rho P, rho T at fixed V, and we have minus rho S by rho PT, which is rho V, rho T. From here we can, and since we have also told that we have to measure the thermodynamic property with respect to the measurable quantities, temperature, pressure, etc. And this actually suggests something interesting, which says that S equals to S hat Vt. That's very interesting, and it also says that S equals to S hat Pt. And having said that, this quantity we need to have in terms of known measurable stuff or known thermodynamic known properties. If we know in terms of known properties, we can measure the derivative, partial derivative, which is dou S dou V at fixed T and dou S dou V at fixed T. These things, for example, this talks about temperature as a function of volume and entropy, and volume as a function of entropy and pressure. That may not be relevant because that we don't need actually. We always like to need the properties, the function of temperature, pressure, or temperature, volume, because these two are actually independent at a time. These two are actually independent at a time. So, for example, if you say for ideal gas, we have PV equals to RT, and we have V equals to V hat. Okay, we have V equals to V hat P. Similarly, so you can see that from equation of state, material property, if we talk about equation of state, from there we can write V equals to V hat Pt, or you can write P equals to V hat Vt, and so on. So you can write from here P hat Vt, and that shows up here. You can see here this S equals to S hat P is nothing but P equals to P hat Pt. With that property estimation, if you look at this, depending on the P hat Vt, and that depending on that V hat P, right? That depending on the V hat P. So, so our objective is to get the derivatives, which are dou s, dou v at fixed t, dou s, dou t at fixed v, dou s by dou t at fixed t, dou s by dou t at fixed v, dou s by dou t at fixed v, dou s by dou v at fixed v. Okay? How to derive, how to get it, and this is very important. If you know how the entropy is changing with volume at fixed temperature, then it is easy to evaluate because in any room temperature volume will change, and with that you can calculate the change in entropy, changing temperature volume, or if there is a change in temperature at constant pressure, for example. If you want to know how the entropy changes, how the entropy is varying with temperature, when the pressure is constant, in that case, those derivatives, if you can evaluate, that will be really helpful. So, before evaluating this, we have to list out what are the things we know and which you can apply, so that these derivatives can be easily evaluated. These derivatives can be easily evaluated. Okay? So, for example, by definition, we know many things, which is dou u by dou t at fixed v, which is what? Dou u by dou t at fixed v. Dou u by dou t at fixed v. Yes, Cv. Correct. Okay, and that says that u also the function of temperature and volume, T and V, is a function of T and V. Similarly, we know that dou h by dou t at fixed P equals to Cp, which is h equals to h at T. That means we have, from definitions, it is known that, basic definition, you know that u is the function of temperature and volume, and dou u by dou t V can be evaluated, dou h by dou t T can be evaluated. And then, from Maxwell's relationship, we have the two other things. What is the dou s by dou v at fixed T? Maxwell's, there are four relationships. Last two relationships are quite useful. They are basically called as isothermal condition relationship. They are called as isothermal condition relationship, which is dou s by dou v at fixed T and dou s by dou p at fixed T. So, minus dou s by dou v at fixed T. So, dou s by dou v at fixed T, from definition, dou s by dou v at fixed T, which is dou p dou dv. The question is, if we see these right hand sides are known earlier, so you can easily say that okay, these quantities you can actually measure change in internal energy with respect to temperature at fixed volume, and you can say that it is nothing but Cv. Okay, Cv is a particular temperature, and sometimes Cv is a function of temperature. All those things will actually come. But if Cv is constant, then you can say this is nothing but change of internal energy with respect to temperature at constant volume. That is nothing but changing internal energy, changing internal energy at constant with temperature at constant volume. Similarly, if we know Cp, we can say that okay, we can if we know Cp, that means what? If Cp is constant, if h versus t, if we know the curve and the slope, you can actually find out, and that slope at constant pressure, which will be Cp. If Cp is constant, a particular temperature, or or if you can go different temperature, you can get different Cp for the curve. If the Cp is constant, we can get straight line, and if it is a curve, so you can get each point different Cp. So we got some kind of information about these derivatives, not all. Because, for example, if I ask dou u by dou v at constant temperature, what is that? You don't know. Dou u by dou v at constant T, you have to find out. The point is, now I'll supply all the informations, all the definitions, Maxwell's relationships are there, definitions are there, and based on that, the question is it possible to find out? Okay. The question remains here. Dou p dou t at fixed B, is it possible to evaluate. For example, another thing is dou S by dou P at fixed T, which is dou V by dou T at fixed P. Can we evaluate these quantities? The question is, the right hand side here we don't know, but how to evaluate these two derivatives? Because if we evaluate these two derivatives, it is possible to have the quantification, which is dou S dou V at fixed T or dou S dou P at fixed T. Now I will talk about some other property like CV, Cp. Some other properties also available for the materials. They are like volume expansion coefficient and compressibility. Okay, so let's talk about volume expansion. Do you remember what is volume expansion coefficient? We have done alpha, beta, gamma. Alpha equals to beta by 2, gamma equals to gamma by 3. So, how to define this volume expansion coefficient? How to define the volume expansion? If I say this beta, 1 by V not B, dou V, dou T at constant pressure. Okay? 1 by V, dou T at constant pressure. Beta equals to 1 by V, dou T at constant pressure. And then other term is there, isothermal. What is there? Anything wrong here? Is there anything wrong? Okay. What is that? Minus here. Yes, I don't know. If I am wrong, then that's it. Am I wrong? Okay. Isothermal compressibility, which I call as kappa. Compressibility means what change we actually see. Expansion means the independent varying gross temperature. Pressure. So compressible means we actually apply pressure. If we increase the pressure, that means we'll do like this. That means we are increasing the pressure. If we expand like this, that means we are reducing the pressure. Pressure is less. If you do like this, any materials will shrink. That means the volume will be decreased. And in that case, this quantity has to be positive. And we have to write minus 1 by V, dou P at constant temperature. Okay? So that's the way one can remember beta and kappa. Beta and kappa, that's volume expansion, isothermal compressibility, one can remember. Okay, so with this information, can you evaluate this? Of course, this can be evaluated, but I will be talking about dou S by dou V at constant temperature. So, dou S dou V at constant temperature, dou S dou V at constant temperature, which is dou P dou TV. We know only volume expansion coefficient. We know only isothermal compressibility. With that, can we evaluate? Yes?
Sir, by cyclic rule we can...
Cyclic rule we have not learned in this class. And I don't apply. We know only two things. One is implicit function theorem and one is chain rule of differentiation. Chain rule of differentiation, how can you do that? Implicit function theorem, if we apply, you know implicit function theorem, we have done it, right? If y equals to if z equals to z hat xy, you can write this as y equals to y hat xz, and we found two conditions. They are called as implicit function theorem rules. That means it says that p is the function of p and t. Can we express this as p is the function of p and t? In that case, you get the ratio. This one. What is that? Minus dou V by dou T. Dou V by dou T. Anybody else? Dou V by dou V. Then cancel, no? Please raise the hand, otherwise I am lost. Please don't talk. Please, please bear with me. I am sorry for that. To request not to talk, because if you talk much, I will be confused.
Dou V by dou P at constant T divided by dou V.
Just slowly, please, because I am not that much fast like you. Dou V by dou P at constant T divided by
dou V by dou T.
Dou V by dou
T at constant T.
Is it correct?
Is the reverse?
Reverse. Dou V by dou C
Dou V by dou T
at constant T.
constant P.
Dou V by dou P at constant T.
Dou V by dou P at constant.
Beta.
Okay. So this is obtained from your this. So that means here this says that P is the function of Vt, and I am writing here V is the function of Pt. When can you write this? If you look at the pressure function in volume, if V is increasing, pressure is decreasing. That's the kind of thing. If you invert it, you get some other function, right? There may be some materials you get then maybe we don't know. If this function is there, can we write this expression? Why? Because if you do V versus P, we will get like this. That means in this zone we have got two values. That means your function V is not uniquely defined for a constant pressure. Implicit function theorem cannot be applied. Implicit function theorem cannot be applied if at this point, but for this case, if you invert it out, still you can get a unique function. Okay? If you invert it, that means if you have V versus P and V infinity, so you get P is 0 and V will be infinite, so we will also get like this, right? Yes? Yes? And P is infinity means, so this is V is tending to 0, P is infinite. So you will be getting unique value, but here you are getting something different. Okay? So that means here, for the ideal cases, for our usual gas laws or real substances, where this kind of relationship actually is valid, you can apply this implicit function theorem. But if there is a material, for example, density versus temperature, what is that? Volume versus specific volume is nothing but density, right? This is what specific volume, right? Okay. Can you think about some material which can have this kind of profile? What I am saying that this is dou V by dou T at fixed speed. You can get from here at a particular pressure. Okay. Can I say? Sorry. Can I write this from this data? Can you have some material which will follow this? That's what I am saying. Pardon?
Thermoplastics.
This is very high formula. Something we actually see every day. Yeah, please don't discuss. If you have any comments, you raise the hand. I appreciate your answer. Yes. Can you have an answer? Yes. You tell me. Yes, you are right. Water. What temperature it behaves? Huh? Yes. For that region, you cannot apply implicit function theorem. So entire violation of thermodynamics of around 4 degrees of water because of this behavior. So once this dou V by dou T, these things you cannot write properly, so most of the things will actually go. Okay. So you cannot invert, you cannot do implicit function theorems, and many of the relationships, for example, if you want to measure dou S by dou V at fixed temperature, you cannot apply this principle, and you have to really investigate thoroughly how to do that, because you cannot have implicit function theorem, because this dou T by dou V at fixed P, we cannot have the unique relationship and the thermodynamics will be valid. Okay, so that's the issues of implicit function theory. Okay, so with that, so much of philosophical perspective at this point. So dou S by dou V at fixed T is how much is that dou V by dou T at fixed P? Minus beta V, and this is minus kappa V. So minus minus plus, and this V by V will go this beta by kappa. That means now we know that AC is the function of volume and temperature, and if we know the ratio of the volume expansion coefficient and the isothermal compressibility, it is possible to have the rate of change of entropy with respect to volume at fixed temperature. Similarly, dou S by dou Pt, we can see dou V by dou T P, and this is nothing but beta V, correct? Minus beta V. So dou S by dou Pt, so I can say that dou S by dou Pt equals to minus beta V. So we got 4 definitions. Please highlight this one in your notebook. First definition, second definition, third definition, and we have got 4th definition. So with this definition, we can proceed to find all possible derivatives with respect to measurable properties like temperature, pressure, and volume. All possible, because one has to know how the internet is changing with respect to volume at constant pressure. For example, in that case, we can easily find out by using all those calculus, implicit function theorem, chain rule of differentiation. One can easily find out. So let me start with 2 derivatives first. Okay, delete this part and keep this part here. Mostly using this and using this. So I'll be having a handful of formulas. This, and there are 4 definitions. We have 4 definitions and we have got this formula. Okay. With that, I want to find dou S, dou Tv, and dou S, dou Tp. First is 2. How to approach? You know what are the formulas we have. How to approach? If you don't know anything, it is better to approach from the very first basics. We know that du equals to Tds minus Tdv, and it says that ds equals to 1 by T du plus T by T dv. Right? Clear? And this suggests that S is function of QV. Very basics. Very basics. Now we have to express your final function is S bar TV. The final function is S bar TV. That means it can be reachable by S hat if you can write this as TV V, and then final function is this. Yes. And now you know how to do it. You apply your chain rule of differentiation, which is dou S dou T at fixed V. Dou S dou T at fixed V. What should you get? How to get it? We remember the formula. ds, if we apply here, if you don't know, ds is dou S hat from here, dou U V du plus dou S hat dou V and then you have dou S dou TV, which is dou S at dou UV dou U dou TV plus dou S at dou VU dou V, not dV, not dou V, not dV, dou V by dou T at fixed V. Very simple. Very simple. Second term will go, right? Because constant V, dou V dou T, this term will go, and dou S by dou U at fixed V, we know from here, T, which is known from here, T, right? Right? So 1 by dou S by dou, sorry, 1 by T, yeah. So, and dou U by dou T at fixed V, CV. And this is dou S by dou U at fixed V. So this gives, or this from here it is obtained dou S by dou U at fixed V equals to 1 by T. You can put it here and you get CV by T, which is dou S by dou T at fixed V. Fun clear? It's very simple. Now you can see by Abelian relationship, now we got very nice thing, dou S by dou T at fixed V is nothing but CV by T. CV is known, the temperature is known, we can calculate dou S by dou T at fixed V. Right? Next is dou S by dou T at fixed P. How to get it? Let's see whether you can give me the answer. We have evaluate dou S by dou T, dou S by dou T at fixed P. Dou S by dou T at fixed P. How to start with? If you say S equals to, I'll see. If I am in your position, you will say, sir, S equals to S at UB. Will that be applicable? Because your final objective function is S bar TP. That means you have to write this as UTP, VTP, and then going back. Do you know any U as a function of T and P? Any formula is available? Yes or no? Check your formula, the right formulas. Check your formula, whether you have any formulas available. You have any formulas, please check it. Anything is there? Nothing is available. Yes, you are right. Correct. Your answer is correct. Nothing is available. Yes, you are also correct. Nothing is available. So then how to approach?
G as a function of
Pardon?
G as a function of
We won't go as G because how to get G from here? You have to get from here, no? This is my basic. How to get G from here? H, yes. Who said H? Great. Okay. So, you can write dH equals to TdS plus VdP, and you can write TdS equals to dH minus VdP, and ds equals to 1 by T dH minus V by T dP. What does it mean? S equals to, it suggests that, so that means from the massive, so we are actually using the massive set. We are using here first time massive set. Massive function will be what? So, massive function will be differential of H by T, so you can actually write something like that, which is S equals, so S is the function of H and T. Am I correct? From here, dH equal to TdS plus VdP, sorry, and from here it suggests that S is nothing but S hat HP, right? Yes? Yes? Any confusion? Yes? Okay. Now, your objective is again what? You have to write S bar Tp. This will not give any help to you. You have to come to this path. To come to this path, S hat H hat Tp P, and then only you can go here. Right? And this is available from definition. Dou H by dou T at fixed P is Cp. That is available. So I can go by this path. So this is the way your conception will be. When you want to take derivative, you have to see how you order it and what are the things available, and based on that. So from here again you can write ds as dou S dou H fixed P dH plus dou S dou P fixed H dP, and dou S dou T at fixed P, which is dou S dou H fixed P dou H dou T fixed P dou S dou P fixed H dou P dou T at fixed P. Am I correct? This is gone. Dou H by dou T at fixed P is Cp, and from here you can see that this is the nothing but dou S by dou H at fixed P, which is 1 by T. So dou S by dou T at fixed P is Cp by T. Dou S by dou T at fixed P is Cp by T. Correct? Yes? Yes? Okay. So dou S by dou T at fixed P is Cp by T. Next, I will go for another two derivatives. Let's see how we can approach. Dou S by dou P dou S by dou P at fixed V. Dou S by dou P at fixed V. And dou S by dou V at fixed P. These two you have to evaluate. Dou S by dou P at fixed B and dou S by dou V at fixed P. You need to evaluate. How to approach? By now we know that S equals to S hat Vt, right? Because previous expression you got dou S by dou T at fixed B equal to Cv by T. Previous expression you got dou S by dou T, and this suggests that this is nothing but S equals to S at Tv. So S at Tv or Vt is known, which is dou S by dou T V is Cv by T. So I can directly write. So now your situation is very simple. And your final function is S bar PV. That means that you can actually obtain by what root? S hat of how to get PV? Yes. D as a function of and V is given remain intact, right? Okay. So V P hat PV, and will go like this. And these functions is known. Dou T by dou P at fixed B from the beta kappa. All those things will come now. So you already know that this is a function of temperature, function of pressure balloon. I am assuming that I am not talking about the water at 4 degrees centigrade. The water at 4 degrees centigrade, then this quantity you can see that it will be drastically affected. I cannot use this formula for water at 4 degrees centigrade, then it will be very particular for different ranges. Then you can suggest the formula, okay, this formula is valid up to 4 degrees centigrade, beyond 4 degrees centigrade, different formula, different function will be applicable. Okay? So, again, ds, take this one. First step, who can help me? First step, who can help me? Yes.
So del S by del V.
Dou S.
Dou S by dou V at constant T.
Constant T. dV.
Plus dou S by dou T at constant T.
Dou S by dou
T.
T.
At constant T.
dV. ds.
dt is the last one. dt.
Okay. dt. Next step,
We have to differentiate.
with respect to PV.
So
Dou S
by dou P.
dou P at fixed V. Next step,
Dou S by dou P at constant P.
dou S by dou V at constant V.
Dou V by dou P at constant V.
Dou V by dou P at constant V.
Plus dou S by dou P at constant V.
Dou S by dou T at constant V.
Dou T by dou V at constant.
Dou T by dou P.
Dou P at constant.
Constant V.
That term will be.
That term will go. Yes. Dou S by dou T at constant V you know right now. CV by T. CV by T. This term, dou T by dou P at constant V, we don't know. But we can use which theorem? Implicit function theorem. If you do that, what you do get? Or we can directly write this as dou P by dou T at constant V. Can you do that? That also is possible. There are two rules in implicit function theorem. Second rule I am applying, which is reciprocal, right? Derivative. Reciprocal derivative. So dou P by dou T at constant V. Okay? Correct? What you get from here? Dou P by dou T at constant V. Beta by K. So what is the final form? CV. Now you can see how easy to evaluate all those derivatives. Okay? All those things are not covered in undergraduate level, right? In a systematic manner. Okay. Next is dou S by dou V at fixed P. Now you know how to do it. Okay? Dou S by dou V at fixed P. Dou S by dou V at fixed P. So it suggests that S has to be function of P and V again. Should we start from here? Yes or no? Yes, let's see. Let's see. If we start from here, our final objective function is PV, and we have to write this as V E PV. Or, yeah, if you do that, what you get? Or one more root I am giving. S equals to S hat P. I think I am not correct. I have not done correctly. V is the function of EP, but I think I am not able to get it from here. Can I get? Yes or no? Think about it. Because this is the function of T and P. This is the function of P and V. But T is remaining, no? Okay, I won't change it. Is that correct? Yes? Okay. ds equals to, there are another root also that I will discuss that part. ds equals to we will volunteer. ds equals to just one hand please, otherwise I get confused. One hand. Who can volunteer? Just yes, thank you sir. Yes sir. Dou S by dou V at constant. Yes sir. Yes sir. Constant V dt. Next. Dou S by dou T. Dou S by dou dou V. Yes. At constant P. Dou S by dou Vt. Dou V by dou Vt plus dou S by dou Tv. Dou T by dou V constant P. This is going on. Dou S by dou V by dou S by dou Vt is, it is obtained here. earlier. Rho S by dou V at constant T is it obtained? It is obtained earlier.
Yes, sir. Beta by kappa.
Beta by kappa definition. This is definition part. Beta by kappa. Dou S by dou T is obtained. CV by T. Dou T by dou V at constant pressure. How to get it? You have to apply all theorems, implicit function theorems or whatever. If you write in reciprocal form, this 1 by dou V by dou T at constant P. What is coming? What is that coming? You will get another kind of formula. Okay, this is one formula you got. This is correct? Agreed? Agreed? Yes or no? Devan, you are not agreeing?
No, I'm just.
Yeah, if you can take reciprocal,
Yeah.
that is from implicit function theorem number 2, you can get beta V. But now we are saying that you can also, instead of starting S at Bt, you can do S equals to S at Pt also, because by now we know that dou S by dou P, dou T, all those things are done. If we approach from here, what will you get? 2S, no? From here also you can write this as, this as function of P and V, and you get S bar PV. What will you get? Will you get the same result? I am waiting for you. So let's see what result you are getting if you apply. From here, what will you get? Dou S by dou V at constant pressure. What will you get? Dou S by dou V at constant pressure. What will you get? Any luck? Because you can go with the same procedure, what I was doing, and from there you can get it.
CP by T into 1 by beta.
CP by
CP by
T beta V.
T beta.
CP by, you are getting different, right? One is this and one is this. So that means, are they different? That means internal analysis is wrong. We are getting two different results. There cannot be two different things, because entropy is a property which should not be dependent on path. Here my path is different. Here one path, here another path. It should not depending on the path. We are getting two different formulas. Both are correct. You can hear it is I have done. There it is you have done. We both are correct. Because, okay, I'll take an example for ideal gas. Cp minus Cv equals to R. Okay? And if you apply that, you see that both are equivalent. So Cp minus Cv equals to R. If you put that here and get all the jugglery, then you can, and for ideal gas, Pv equals to RT, and from here we can get all the relationship, and if you plug it in there, you go back home, plug it in there, both are equivalent formulas. Both are equivalent formulas. Okay? So, and for real gas also you have this kind of formula. If you take Van der Waals gas, or if you take the Payne-Robinson equation of state, or Soviet-Bentley-Cohen equation of state, or so many equations of state are available, SRK, Payne-Robinson, whatever you apply, when you apply this another formula for any of the properties, This kind of property is also applicable to the real substances. If we apply it, you see this will be the same. So another formula is also available. So we have to be implementing the properties. We have to be implementing the properties so that we can evaluate the derivatives. Okay.